Welcome back to the Deep Dive. Today we are tackling a topic that it feels like it should be the most intuitive thing in the world. Yet somehow, when you open the textbook, it manages to be one of the most mathematically intense chapters in the entire NISM Series XA certification. We are looking at Chapter 14, Introduction to Modern Portfolio Theory.
It is a fascinating contradiction, isn't it? It takes perhaps the oldest piece of financial advice in human history, don't put all your eggs in one basket, and it completely transforms it. It asks a very specific and actually a very difficult question. We all know we should spread the eggs around, but how do you actually measure the benefit of doing that? Is there a number for it? Can we quantify safety?
Exactly. I mean, my grandmother told me not to put all my eggs in one basket. It's pure folk wisdom, but she never told me how to calculate the covariance of the eggs or, how to plot those eggs on an efficient frontier to maximize my omelet potential.
I'm going to go out on a limb and assume she didn't use the word covariance at the kitchen table.
She definitely did not. And that is exactly what we are doing today. This is a deep dive specifically designed for the NISM Series XA exam. Our mission is simple. We are going to replace the need for you to read the PDF. We're going to walk through Chapter 14, section by section, ensuring you understand the history, the assumptions, the heavy math. And yes, I'm warning you now, there is math and the optimization process.
But we aren't just going to recite formulas. That's not the point. We are going to deconstruct them. We want you to understand why the formula exists in the first place. So if you are driving to work, hitting the gym, or just sitting at your desk trying to make sense of this certification, keep listening. By the end of this, you'll be able to explain concepts like certainty equivalent rate and estimation risk, like a seasoned portfolio manager.
Let's look at the roadmap for the session. We're starting with the history, the origin story of these ideas. Then we'll move to the 5 key assumptions that hold the whole theory together. After that, we get into the mechanics, the calculation of risk and return for individual stocks, and then for portfolios. Finally, we'll talk about the efficient frontier and, well, the problems with implementing this in the real world.
It is a full agenda. So let's jump right in with section 14.1, the framework.
Okay, let's unpack this. The text starts by defining diversification. It says, diversification is nothing but spreading out the investments across different areas or asset classes to reduce risk. That sounds pretty standard. We've heard that a million times. But then it adds a crucial qualifier, as every asset will not behave similarly at all times.
That is the sentence that changes everything, as every asset will not behave similarly.
If you miss that part, you miss the whole point of modern portfolio theory. Think about it. If you buy 10 different banking stocks, have you diversified? Well, intuitively, I want to say yes.
Yeah.
I mean, I own 10 different companies. I've spread my capital out. If one bank goes bust, I still have 9 others.
That is the eggs in a basket logic, but it's flawed. Because what happens if the Reserve Bank of India, the RBI, suddenly raises interest rates by 2%? Or what if there's a systemic crisis in the lending market? What happens to all 10 of those banks?
They all crash.
Exactly. They all move in the same direction at the same time. You haven't diversified your risk. You've only diversified your paperwork. You still have 100% exposure to what we'd call the banking factor.
So in the Indian market context, if I hold HDFC, ICICI, SBI, Axis, and Kotak, I'm basically just holding one giant banking position. But if I hold HDFC, Sun Pharma, and TCS.
Now you are thinking like a portfolio manager. You have banking, you have pharmaceuticals, and you have IT. These are 3 very different sectors. If banking regulations get tough, pharma might still be doing well because, well, people always need medicine. If the rupee strengthens, IT might struggle because their exports become more expensive, but the domestic banks could be rallying.
So the goal isn't just buying many things. It's buying things that don't hold hands and jump off a cliff together.
Precisely. You are looking for assets that behave differently. That is the essence of the framework. Diversification isn't about quantity, it's about the correlation between the assets.
Now, the text gives us a bit of a history lesson here, and I feel like there are some potential exam questions hidden in the dates. It mentions that prior to 1950, diversification was known, but not quantified.
Yes, and that's a key distinction. Before the 1950s, investment management was more of an art than a science. It was based on intuition, gut feeling, maybe some insider knowledge. People knew they should spread their bets, but they couldn't tell you exactly how much risk they were reducing by adding a second or third stock.
And then came 1952.
1952 is a watershed moment. You absolutely need to flag this date for the exam. This is the year Harry Markowitz published his article titled Portfolio Selection in the Journal of Finance.
Harry Markowitz, the father of modern portfolio theory, or MPT.
That's him. He looked at the market and essentially said, "We are looking at this all wrong." Before Markowitz, people looked at the risk of a stock in isolation. They'd ask, "Is Tata Motors risky?" Markowitz said, "It doesn't matter if Tata Motors is risky on its own. What matters is how Tata Motors interacts with the rest of your portfolio."
He changed the unit of analysis from the stock to the portfolio.
Correct. And to do that, he introduced the statistical notion of correlation and covariance to actually measure that interaction. He was the one who proved that the variance of the rate of return is the meaningful measure of portfolio risk.
There was a second date mentioned in the text. It's a big jump forward. 1990.
Yes, nearly 40 years later. In 1990, Harry Markowitz wins the Nobel Prize in economics for this theory.
That seems like a really long wait.
It was. But it often takes time for radical academic theories to become the standard operating procedure for an entire industry. By 1990, MPT was everywhere. Every fund manager, every analyst was using his framework. So for the exam, if they ask for the foundational paper, the answer is 1952. If they ask when MPT was recognized with a Nobel Prize, the answer is 1990.
Got it. 1952 for the paper, 1990 for the Nobel. Markowitz is the guy. Now, for any theory to work, especially a mathematical one that tries to model human behavior, you have to set some ground rules. Section 14.2 lists the assumptions of the theory.
And this is often where students' eyes just glaze over. Assumptions sound boring, they sound like the fine print, but you cannot afford to zone out here. The exam loves to ask negative questions.
You mean questions like, which of the following is not an assumption of MPT?
Exactly. If you don't know the list, you are just guessing. There are 5 main assumptions listed in the text. We need to go through these one by one and really understand what they imply about how MPT views the world.
Let's do it. Assumption number 1. An investor wants to maximize the return for a given level of risk.
This is the assumption of rationality. It sounds obvious, right? I want more money, not less. But it's actually a very strict rule. It means that investors are consistent and predictable.
Can you give me an example of what that means in practice?
Sure. Imagine I offer you 2 mutual funds, Fund A and Fund B. Both of them are equally volatile. Let's say they both swing up and down by about 15% a year. They have the exact same risk profile. However, Fund A gives an average return of 12%, and Fund B gives an average return of 15%.
I'm taking Fund B. Every single time, no question.
Of course you are. You would never choose Fund A. Why would you take less money for the same amount of stress? That is what this assumption means. It implies investors are risk-averse. They dislike risk. They will only accept risk if they are compensated for it with higher returns.
But in the real world, people aren't always rational, are they? I mean, maybe my cousin manages Fund A, so I buy it to be nice. Or maybe I just like the commercials for Fund A better.
Exactly. Real humans have biases, emotions, social connections. But MPT assumes none of that exists. In the world of MPT, you are a cold, calculating machine that only looks at risk and return numbers. The moment you pick Fund A, the model breaks. So, assumption 1 is, we are rational maximizers.
Okay, assumption number 2. Investors maximize one period expected utility. What does one period mean here?
This is a simplification to make the math workable. It means the model looks at a specific horizon. Maybe it's 1 year, maybe it's 5 years. But the investor is making a decision now to maximize their satisfaction or utility at the end of that specific period.
So we aren't constantly changing our minds every day.
Right. We aren't day trading in this model. We are setting a plan for a period. And we assign a score, that's the utility, to the possible outcomes at the end of that period. And we pick the portfolio that gives us the highest expected score.
That word utility comes up again in assumption number 3.
Yeah.
Utility curves demonstrate diminishing marginal utility of wealth. That is a mouthful of economic jargon.
It is, but the concept is actually very intuitive. It basically asks a simple question. How much happiness does money buy you?
I'd say a lot.
But does the millionth rupee buy you as much happiness as the first rupee?
Okay, I see where you're going with this. No.
Let's use a relatable example. Imagine you are a broke college student. You have 0 income. You are surviving on instant noodles. If you are walking down the street and you find a 500 rupee note on the pavement, how do you feel?
I'm ecstatic. I'm throwing a party that's huge, that's food for a week. The utility of that 500 rupees is massive.
Exactly. Now, let's switch roles. Imagine you are Mukesh Ambani. You are walking down the same street and you see the same 500 rupee note.
I probably wouldn't even stop to pick it up. It's not worth the back pain. The utility is basically 0.
Precisely. The money is identical. It is the same piece of paper with the same purchasing power, but the utility, the satisfaction it provides has diminished because you already have so much wealth.
So diminishing marginal utility means that as your wealth increases, each additional rupee brings slightly less satisfaction than the previous one. The curve flattens out.
Correct. And this explains why people are risk-averse. Think about it. If you have 10,000 rupees, losing it hurts more than gaining another 10,000 rupees feels good. The pain of loss is greater than the joy of gain because of this utility curve. That is a fundamental pillar of the theory.
That makes perfect sense. Okay, on to assumption number 4. Investors estimate the risk of the portfolio on the basis of the variability of expected returns.
This brings us right back to Markowitz. In MPT, we need a number for risk. We can't just use a vague feeling of danger. So Markowitz defined risk as variability.
Variability meaning how much the price jumps around.
Volatility. Yes,
Right.
exactly that. Volatility. If a stock goes up 1% every single day like clockwork, it has zero variability. It is risk-free in this model. But if a stock goes up 10% one day and down 8% the next, it has very high variability.
So in the language of this chapter, risk equals standard deviation.
That's it. We don't define risk as the company might go bankrupt or the CEO might quit. We define it purely as the statistical spread of the returns.
And finally, assumption number 5. Investors base decisions solely on expected return and variance.
This is what I call the blinders assumption. It reinforces what we said earlier. Investors don't care if a company is green or ethical or makes cool products that their friends use. In the world of MPT, every single asset is reduced to just two numbers: the mean, which is the expected return, and the variance, which is the risk.
So if a tobacco company and a solar energy company have the exact same risk and return numbers.
To a pure MPT investor, they are identical. They're interchangeable. You are indifferent between them. It's a purely mathematical world.
Okay, so we've got the history and the ground rules. Now, section 14.3 dives into investor risk profiles. It acknowledges that while we assume everyone is rational, not everyone has the same tolerance for pain.
Right. We are all risk-averse to some degree, but some are more averse than others.
Before we get to the profiles, the text defines something called a fair game. This seems like a baseline concept we need to understand.
It is. A fair game is a prospect that has a zero-risk premium. Think of it as a simple coin toss with a friend. I say, if it's heads, I give you 100 rupees. If it's tails, you give me 100 rupees.
Okay, so I have a 50% chance of winning 100 and a 50% chance of losing 100.
The expected value is 0. In the long run, you break even. You aren't getting paid any extra to take the risk of losing your money. That's a fair game.
So how do different investors react to this fair game?
Well, let's start with the most common one, the risk-averse investor. This is the standard assumption for all of MPT. A risk-averse investor rejects a fair game.
I would. Why would I risk losing my hard-earned 100 rupees just to potentially win 100? The utility of losing the 100 is greater than the utility of winning the 100, like we just discussed.
Exactly. You demand a risk premium. You need the odds tilted in your favor. Maybe if I said if it's heads, you win 200, but if it's tails, you only lose 100, then you might play. You need a positive expected return to take on that uncertainty.
This brings us to a term that I know is absolutely critical for the exam. Certainty equivalent rate, or CER. Can we break that down?
Yes, please flag this. It is a concept that students often struggle with, but it's actually quite simple if you think about it as a price. The certainty equivalent rate, or CER, is the rate that a risk-free investment must offer to be considered equally attractive as a risky portfolio.
Okay, can you give me a concrete example?
Sure. Let's say I offer you a risky stock portfolio. Based on our analysis, it expects to return 12% next year. But it's volatile. It could tank. It's stressful to hold.
Okay, so I have a risky 12%.
Now, imagine I also offer you a fixed deposit, an FD, in a government bank. It is 100% risk-free, guaranteed. The question is, what interest rate would that FD need to pay for you to say, you know what, I'm indifferent. I'd be just as happy with the FD as I would be with that risky stock.
Well, since I hate risk, I wouldn't demand the full 12%. I'd be happy with less. I might say, if you give me a guaranteed 8%, I'll take the FD. The peace of mind is worth that 4% difference.
Then your certainty equivalent rate for that risky portfolio is 8%. You have effectively discounted the 12% expected return by 4% to account for the pain or the stress of the risk.
I see. So the CER is basically my happiness price. It's the guaranteed return that makes me just as happy as the risky one.
Exactly. And the text points out a highly risk-averse investor will assign a lower CER. They're so scared of risk that they might say, I'd rather have a guaranteed 4% than a risky 12%. A less risk-averse person might say, I'd need at least a guaranteed 10% to give up that shot at 12.
Okay, what about the risk-neutral investor? That's the second type.
The risk-neutral investor is like a robot. They evaluate solely based on expected return. Risk is completely irrelevant to them. For them, the CER is equal to the expected rate of return. If the stock expects to return 12%, they value it at 12%. They don't penalize it for volatility at all. They would play that fair game coin toss all day long because the expected loss is zero.
And finally, the third type, the risk-seeking investor.
The gambler. They are willing to engage in a fair game, and sometimes they're even willing to pay a premium to take on more risk. They make an upward adjustment for utility. They get a thrill from the risk itself.
Like buying a lottery ticket. The expected value is negative, but people buy them for that tiny chance and the excitement.
Exactly. But for the purpose of the NISM exam and MPT, we almost always assume the investor is risk-averse. We want to be paid for our risks. That's the default human condition in finance.
Got it. We are risk-averse. We want payment for our pain. Now let's get into the mechanics. Section 14.4 is titled Calculation of Expected Rate of Return for Individual Security. Time to do some math.
We do. And the text provides a very clear example using scenarios. This is actually how analysts work in the real world. They don't just guess a single number. They look at different possible economic states.
The table in the text lists 3 scenarios: boom, normal, and recession. In a boom, which has a probability of 0.3 or 30%, stock A returns 15%. In normal times, probability 0.5 or 50%, stock A returns 10%. And in a recession, probability 0.2 or 20%, stock A returns just 2%.
Right. So to find the expected return, you calculate the weighted average. It's a simple sum product. You multiply the probability by the return for each row and then add them all up.
Let's walk through it. For the boom scenario, it's 0.3 times 15, which is 4.5%. For the normal scenario, it's 0.5 times 10, which is 5.0%. And for the recession, it's 0.2 times 2, which is 0.4%.
Now, you just add those up. 4.5 plus 5.0 plus 0.4 equals 9.9%. So the expected return for stock A based on these probabilities is 9.9%.
That seems straightforward enough. It's just weighting the outcomes by how likely they are to happen. But now we get to the tricky part. Risk. The text defines risk as variance and standard deviation.
Yes. Remember assumption 4. Risk is variability. To calculate this, we need to measure how far the actual returns in those scenarios stray from that 9.9% average we just calculated.
The text outlines a 7-step process for this. It looks like a table you'd build in Excel. Step 1, list the yearly returns. Okay, step 2, compute the mean or the average. We just did that. It's 9.9. Step 3, subtract the mean from each year's return. This is the deviation.
Let's pause on step 3 because it's important. In the boom scenario, the return was 15%. The average is 9.9, so the deviation is plus 5.1%. In the recession scenario, the return was 2%. The deviation is minus 7.9%. Some years you do better than average, some years you do worse. If you just added these deviations up, they would cancel each other out, and the sum would be 0. That doesn't help us measure risk.
Right, so that leads to step 4, square each year's deviation.
Exactly. By squaring the numbers, we make everything positive. Negative 7.9 times negative 7.9 becomes a big positive number. This does 2 things. It removes the negative signs, and it penalizes large outliers more heavily. A big crash becomes a massive number in the calculation, which is what we want.
Step 5 is add all the values. Step 6 is divide the sum by the total number of periods minus 1 and 1. Why minus 1? Why not just divide by n?
That is a statistical adjustment called Bessel's correction. It applies when you are using a sample of data to estimate the whole population's variance. It just makes the estimate more accurate or unbiased. Just remember for the exam, if you are calculating variance from a sample of historical years, you divide by n1, not n.
Okay, n1. Got it. And the final result of that division is the variance. In the example provided in the text, the variance comes out to 88.3.
But 88.3 what percent squared? Bit of a weird unit.
Yeah, that's not intuitive at all. My risk is 88% squared. Nobody says that.
It's hard to interpret, and that is why we have the final step. Step 7. Take the square root of the variance to determine the standard deviation.
So the square root of 88.3 is 9.40.
And there is your magic number, 9.40%. That is the measure of dispersion. That is the risk. It tells you that on average, the annual return deviates from the mean by about 9.40%. A higher number means higher risk. A lower number means more predictable.
So if I'm comparing 2 stocks, I just look at their standard deviations, and the one with the higher number is the riskier one.
Precisely. It is the universal yardstick of risk in finance.
Okay, that covers individual stocks. But the whole point of this chapter is portfolio theory, mixing things together. Section 14.4 continues into calculation of variance of return for a portfolio.
This is where Markowitz changed the game. Now, calculating the expected return of a portfolio is easy. It's just the weighted average, like we did before. If you have 20% of your money in stock A, which has a 9% return, and 80% in stock B with a 10% return, you just take 20% of 9 plus 80% of 10. Simple multiplication and addition.
But the risk. The risk isn't a simple weighted average, is it?
No. And this is the most critical concept in the entire chapter. Flag this for the exam. Listen closely. Portfolio risk is not the weighted average of the individual risks. It is almost always lower due to diversification.
Because of that diversification benefit we talked about right at the start, the assets not moving together.
Right. And the formula for portfolio variance proves that mathematically. It's a bit scary to look at, but we need to visualize it. It has three main parts. Imagine an equation. Part 1 is the weight of asset A squared times the variance of asset A. Part 2 is the weight of asset B squared times the variance of asset B. So far, it looks like a weighted sum. But then there is part 3, the covariance term.
The text writes this out as 2 times W1 times W2 times 1, comma 2 times sigma 1 times sigma 2. That's a lot.
Let's break that down variable by variable. It's not as bad as it looks. W1 and W2 are the weights, how much you invested in each. Easy. Sigma 1 and sigma 2 are the standard deviations, the risk of each stock. We know how to calculate that. But the star of the show is that little r, that's R1, comma 2. That is the correlation coefficient.
This is the number that tells us how the two assets move together.
Exactly. This r can range from +1 to -1. If r is +1, the assets move in perfect lockstep. When one goes up, the other goes up by the same proportion. The diversification benefit is 0. But if r is low, say 0.5 or 0 or even negative, that entire third term in the equation becomes smaller. It actively shrinks the total variance.
So mathematically, this third term is subtracting risk from the portfolio because the assets don't move together perfectly.
Yes. That is the mathematical proof of don't put all your eggs in one basket. The covariance term acts as a risk reducer. If you have two volatile assets that are negatively correlated, one tends to go up when the other goes down, you can combine them to create a portfolio that is incredibly stable.
The text then escalates this to a 3-security portfolio. It says, in a 3-investment portfolio, there would be 6 terms.
Right. Think about it. You have the variance for A, B, and C. That's 3 terms. Then you have the covariance of A with B, the covariance of A with C, and the covariance of B with C. That's another 3 terms. 3 plus 3 gives you 6 terms total.
And this leads to what I call the correlation explosion. As you add more and more stocks, the number of these relationships just explodes.
Flag this formula for the exam. The text gives a formula for calculating the number of covariance terms, just the relationships. It's calculated as n squared minus n divided by 2, where n is the number of securities.
Okay, so the text uses the example of 50 investments. If I have a portfolio of 50 stocks, so n equals 50, how many covariance estimates do I need?
Let's do the math. 50 squared is 2,500, minus 50 is 2,450, divided by 2 is 1,225. You need 1,225 covariance estimates.
That is massive. That's a huge number of calculations.
It is. It highlights the sheer complexity of implementing MPT in the real world. As you add stocks, the number of relationships between them grows exponentially. You absolutely need a computer to do this. You can't do it on a napkin. This is why Markowitz's theory didn't really take off in practice until computers became powerful enough to handle these huge matrices of data.
Okay, I am memorizing that number. 4,225 for 50 stocks, and the formula, n squared minus n over 2. Now that we have the math, let's try to visualize it. Section 14.5 and 14.6 talk about the graphical presentation and the efficient frontier.
This is one of the most famous charts in all of finance. I want you to visualize a graph. The vertical axis, the y-axis, is expected return. Higher is better, so it goes up. The horizontal axis, the x-axis, is risk, measured by standard deviation. Further to the right is riskier.
Okay, I'm visualizing it. Risk on the bottom, return on the side. Every possible portfolio is a dot on this graph.
Exactly. First, imagine 2 assets, A and B. If they are perfectly correlated, so R equals +1, the possible combinations of risk and return just form a straight line connecting them. You can pick a point on the line, but you aren't getting any bonus benefit. You're just averaging their risk and return.
But what happens when the correlation is less than 1? when there's a diversification benefit.
The line starts to bend. It bends to the left, towards the y-axis. It looks like the curve of a bullet nose or the side of an umbrella.
The text calls this the umbrella-shaped curve.
Yes. This curve represents the benefit of diversification. Because the line bends to the left, there are points on that curve where you get more return for the same amount of risk compared to the straight line. Or you can look at it the other way. You get the same return for less risk.
And this curve, this outer edge, is called the efficient frontier.
Correct. Section 14.6 defines the efficient frontier as the set of optimal portfolios. It's the boundary. You cannot get any better than this curve with this set of assets. Any portfolio that lies on the curve offers the highest possible expected return for that given level of risk.
And what about the points inside the umbrella, below the curve?
Any portfolio that lies below the curve is suboptimal. It's inefficient.
Why is it suboptimal?
Because if your portfolio is a dot inside the umbrella, you are taking on a certain amount of risk, but you aren't getting the maximum possible return for it. You could just move straight up to the curve and get more return for the exact same amount of risk, or move straight left to the curve and get the same return for less risk. Being inside the umbrella is inefficient. You always want to be on the edge.
So as an investor, my goal is to pick a spot somewhere on that efficient frontier line. That's the best I can do.
Exactly. And where you pick depends on your risk appetite. If you are aggressive, you pick a point high up on the curve, high risk, high return. If you are conservative, you pick a point lower down on the left, low risk, lower return, but you always, always want to be on the line.
This brings us to the final section, 14.7 and 14.8, the optimization process and estimation issues. How do we actually build this? What do we need?
The text describes a flowchart for this. To run this portfolio optimization engine, the manager needs 3 specific lists of inputs. We've talked about all of them. Number 1, the expected return of every single asset in your universe. Number 2, the standard deviation or risk of every single asset. And number 3, the correlation coefficient among all of the assets.
So for that 50 stock portfolio, I need 50 return estimates, 50 risk estimates, and those 225 correlation estimates.
Correct. You feed those thousands of numbers into the optimizer. It runs the math using that matrix algebra we talked about, and it spits out the efficient frontier. Then the investor looks at their own objectives, their own risk tolerance, and picks the one optimal portfolio for them from that frontier.
It sounds perfect. It sounds like we solved investing. It's a big math problem. But Section 14.8 throws a wet blanket on the whole thing. It's titled Estimation Issues.
This is the gotcha. This is the big asterisk on the entire theory.
Yeah.
The theory is mathematically perfect, but it relies entirely on the inputs. The text warns that the output of the portfolio allocation depend on the accuracy of the statistical inputs. This is often called estimation risk.
Garbage in, garbage out.
That's the perfect way to put it. Exactly. If your estimate for the future return of Tata Motors is wrong by a few percent, or if you assume the correlation between the tech sector and the pharma sector will stay low, but then it suddenly spikes to +1 during a market crash, which often happens, then your so-called optimal portfolio might actually be a disaster.
The text mentions that calculating all this requires variance, covariance matrix calculations, and suggests referring to a financial modeling textbook by Simon Benninga.
Which is a polite way of the textbook saying, don't try this by hand.
Yes.
It implies that in the real world, this is done via sophisticated software or massive spreadsheets. The math is solid, but the real challenge is predicting the future inputs accurately.
Wow. So we've gone from don't put your eggs in one basket to matrix algebra and 12,225 correlations, only to find out it all depends on our ability to guess the future.
That is the journey of modern portfolio theory. It formalizes our intuition into a rigorous science, but it doesn't eliminate uncertainty. It just helps us manage it.
Let's just do a quick check to see if we hit all our mission objectives for this deep dive. We covered the history. Markowitz, 1952, Nobel Prize in 1990.
Check.
We covered the 5 key assumptions: rationality, utility, risk as variance.
Yeah, all 5.
We defined the investor profiles:
Right.
risk-averse, and the all-important certainty equivalent rate, risk-neutral, and risk-seeking.
Got it.
We did the math. Weighted average returns, variance with the N1 denominator, and standard deviation is the square root.
We did.
We tackled that scary portfolio variance formula and the crucial role of the correlation R.
Yes, the star of the show.
We visualized the efficient frontier and the umbrella,
I do.
and we just finished by warning about estimation risk, the whole garbage in, garbage out problem.
I think we have covered every single inch of Chapter 14. Anyone listening to this should be in great shape for the exam questions on this topic.
Before we sign off, what is the one thing you want the listener to take away from all this? Not just for the exam, but for, their own investing life.
It's that final point. The math assumes we are rational and that markets are predictable, that the future will look something like the past we use to calculate standard deviation. But what happens if the boom-bust probabilities we estimated are just plain wrong? That is the lingering danger of MPC. The map is not the territory. Use the theory to understand why you diversify, but don't blindly trust any model to predict the future perfectly.
That is a very provocative thought to end on. The map is not the territory. All right, listeners, good luck with your NISM Series XA exam. Remember the number 1225, remember the definition of certainty equivalent rate, and remember to diversify those eggs.
Good luck.
We'll see you in the next deep dive.